Welcome to this comprehensive guide on C-sharp error handling, a crucial skill for building robust and reliable applications that can gracefully manage unexpected issues. In the world of software development, errors are inevitable. Understanding how to anticipate, detect, and manage potential runtime issues is absolutely essential for any C-sharp developer. This video will demystify the core mechanisms of C-sharp error handling: try, catch, finally, and throw, making these fundamental concepts clear and easy to grasp for beginners. Let's begin our journey with the fundamental try-catch blocks, which serve as your primary defense mechanism against unexpected errors and exceptions in your code. The try block is specifically designed to enclose any section of code that might potentially raise an exception during its execution. If an exception or an unexpected problem occurs within this try block, the normal flow of execution is interrupted and control immediately shifts to a corresponding catch block. The catch block is precisely where you implement your error handling logic. This could involve logging the error for later analysis, displaying a user-friendly message, or taking corrective actions to recover. A crucial best practice is to catch specific exceptions before more general ones. This allows you to provide tailored responses for different types of errors. Consider a common scenario. Attempting to divide a number by 0 will inevitably throw a divide by 0 exception. In our example, we first catch the divide by 0 exception specifically to provide a precise and informative message to the user. Following this, a more general catch block is included to handle any other unforeseen or unhandled errors that might occur, acting as a safety net. Next, let's explore the finally block, a powerful construct that guarantees the execution of its code, regardless of what happens in the try or catch blocks. The code within a finally block will always run, whether an exception occurred, was caught, or no exception happened at all. This makes it absolutely ideal for critical resource cleanup tasks, such as closing file streams, releasing database connections, or disposing of other system resources. For instance, if you open a stream reader to read from a file, the finally block ensures that the reader is properly closed, preventing resource leaks. Even if a file not found exception occurs during the file reading process, the finally block will still execute, guaranteeing the stream is closed. Now, let's discuss the throw statement, which allows you to explicitly generate an exception within your code. You have the flexibility to throw either built-in exceptions provided by the .NET framework or create your own custom exception classes for more specific context. For example, if a method receives null data when it expects a valid input, you might throw new argument null exception to clearly indicate the problem. When you need to rethrow an exception from a catch block, it's crucial to use throw without specifying the exception object. This preserves the original stack trace, which is absolutely vital for debugging, as it helps pinpoint the exact original source of the error. Now, let's delve into some essential best practices for effective exception handling in C#. First, only catch exceptions that you can genuinely manage, recover from, or at least log meaningfully. Avoid catching errors you can't handle. A critical rule is to avoid swallowing exceptions, which means catching them without any meaningful action or logging. This hides problems and makes debugging extremely difficult. Always handle exceptions at the appropriate abstraction level within your application's architecture. Don't catch low-level errors at a high-level UI component. Implement robust and comprehensive logging using established frameworks like Serilog, Nlog, or Log4net to record all exceptions and critical events. Keep your try blocks as concise as possible, focusing only on the specific lines of code that are prone to failure, improving readability and maintainability. Never, under any circumstances, use empty catch blocks. They completely hide errors, making your application unstable and debugging virtually impossible. Utilize custom exception classes to provide more specific and domain-relevant context about errors, making them easier to understand and handle. Let's now review some of the most common exception types you'll frequently encounter and need to handle in C# applications. Argument null exception occurs when a method receives a null argument where a non-null value is expected, indicating invalid input. File not found exception is thrown when an attempt to access a file fails because the specified file does not exist on the system. Divide by 0 exception happens when an arithmetic operation attempts to divide an integer or decimal value by 0, which is mathematically undefined. Format exception indicates that the format of an argument is invalid or not in the expected pattern, such as trying to convert ABC to an integer. Overflow exception occurs when an arithmetic operation results in a value that is outside the range of the data type being used to store it. Index out-of-range exception is thrown when an attempt is made to access an element of an array or collection with an index that is outside its valid bounds. Now, let's transition to discussing effective error handling strategies that can be applied across your C# applications. Implement robust error handling across your entire application to ensure maximum stability and resilience against unexpected failures. For complex scenarios where different parts of a process might fail independently, consider using nested try-catch blocks to isolate and handle errors more granularly. Establish comprehensive exception logging and monitoring systems to capture, store, and analyze all errors that occur within your application. This proactive approach allows you to quickly identify, diagnose, and address issues in production environments before they significantly impact users. Also, develop specific handling routines for common exception types to provide tailored responses and recovery mechanisms, improving user experience. Finally, let's cover some additional considerations and advanced tips for optimizing your error handling strategies. Regarding performance, try-catch finally blocks themselves introduce negligible overhead during normal, error-free execution. However, frequently throwing and catching exceptions can significantly impact application performance, so use them judiciously. For asynchronous operations, ensure you use try-catch within async methods for proper exception handling, as exceptions can behave differently in async contexts. Implement centralized exception handling for a unified and consistent approach across your entire application, often using global error handlers. This ensures all errors are processed uniformly, improving maintainability and simplifying the overall error management process. Employ specialized error monitoring services to collect, aggregate, and analyze exceptions, especially crucial for production environments. These services provide invaluable insights into application health, performance bottlenecks, and ultimately, the user experience. Adhering to these comprehensive practices significantly enhances your C# application stability, making it more resilient to unexpected issues. It also vastly improves maintainability, making your codebase easier to manage, debug, and update over its lifecycle. Ultimately, implementing robust error handling leads to a much smoother and more reliable user experience, building trust in your software. Thank you for joining this deep dive into C# error handling. We hope this guide has provided you with valuable insights. Mastering these concepts will empower you to build more resilient, professional, and user-friendly applications in your C# development journey.